Welcome, fellow coders. Today, we have an ultra-efficient solution to the classic frog jump problem on LeetCode for you. And the solution we have here? It's written in TypeScript.
That's right. This particular solution stands out, beating 100% of users in runtime and 87% in memory usage. Ready to dive in? Let's go.
The goal here is to determine if the frog can cross the river by landing on the last stone. The solution uses a step-by-step method, remembering past results, to check if the frog can hop across stones by trying different jump sizes and avoiding redoing the same jumps.
At a glance, the function is named canCross, taking in an array of stones as its parameter.
The initial check is simple. If the second stone isn't positioned at 1, the frog can't make the jump, and we immediately return false.
With that check passed, we introduce a memoization set named memo. Memoization helps avoid redundant calculations, thus speeding up the process.
Absolutely. Moving on, the function can is defined recursively and checks for every stone if the frog can cross starting with a certain jump size, k, and from a certain index.
Before diving deep, it's vital to understand the key used for memoization. The key is a string representation of the jump size k and the current stone's index. This allows us to uniquely identify each state.
Right on. As we traverse the stones, we compute the gap between the current stone and the next. If this gap becomes more than the current jump size plus 1, the frog simply can't make the leap. So, we break out of the loop.
And if the gap is within our jump range, which is between k1 and k plus 1, we check recursively if jumping the gap allows the frog to eventually reach the end. If so, we've found our path, and we return true.
But if after all possible jumps the frog can't reach the end, we add our state to the memoization set. This ensures that the next time we encounter this state, we know that the frog can't make it from here and can quickly return false.
Finally, the main function call kicks off the recursive journey with an initial jump size of 1 from the second stone. If the frog can make it across, the function returns true, or else false.
And there you have it. A super efficient solution for the frog jump problem.
With problems like this, understanding the core logic and implementing memoization can often make the difference between a solution that's just okay and one that's top tier.
Thanks for tuning in, and keep coding. We'll see you in the next one.